most awaited moment has arrived now. We have with us the Chairman, Indian Institute of Engineering, Science and Technology, Shibpur, and ex-Chairman of ISRO, Dr. Radhakrishnan, to share the real story behind Mars Orbiter Mission MOM. Dr. Radhakrishnan completed his PGDM from IIT Bengaluru, received PhD from IIT Kharagpur. He has been the chairman of ISRO in Bangalore from 2009 to 2014. Under his direction as chairman at ISRO, 37 Indian space missions, launch vehicles and satellites were executed. Under his effective leadership, India's first planetary exploration, the Mars Orbiter mission, was conceived, planned, and executed with a great deal of originality. Sir has been awarded with numerous accolades, to name a few. Sir received the prestigious Alan D. ML Memorial Award, Distinguished Alumnus Award of IIT Kharagpur and IIM Bangalore, Silver Jubilee Honor by Ministry of Earth Sciences. Sir has been named amongst nature's top 10 people who mattered. Dr. Radhakrishnan also achieved Padma Bhushan Award for his contribution to science and engineering, especially in fields of space science and technology. I humbly request you, sir, to please come and address the gathering.
Good afternoon. I started my day at 4 o'clock this morning and listening to the director IIT, of which I was a student. I felt it was a good thing that I did, and I thank our dean for giving me that opportunity. It was a wonderful talk. I will just put a few slides to introduce the subject on the challenges that we faced, what we went through since August 2010 to execute the Mars Orbiter mission. And one thing which I learned over the last 1 year is that nobody in India need to be told about the Mars Orbiter mission. I went to Kozhikode for a function, and one of the religious leaders, a young man, was explaining to the entire community what the whole thing is about, what was the challenge in Mars Orbiter mission, and after doing this, where India is in the world in this area. I felt very happy at that point of time. That is one part of it. On September 24th, when this major action was done, we had from various parts of the country children coming to the school and watching that event. And after that, we received heaps of postcards, rolls of letters, and clothes on which they had written down several comments, all sent to us. We also had them in the schools making models of how this whole mission was achieved. And we also saw, and you must be also part of it, on the Facebook, which has today 9 likes, discussing physics, mathematics. And one single achievement of this rupees 450 crores investment in the country is that transformation that has taken place in the younger generation of the country. And when we went abroad immediately after that, we found all the Indians who are outside feeling so proud. We went to Canada. Even in the airports, any Indian who saw us wanted to take a photograph. And they said, today we are feeling proud, we are better than Canadians. That's the kind of feeling that you get. So India is proud, India can do. So what I just wanted to tell in a few slides is that story. Can I have the first one? This is basically where we are and where we reached. And a small element of India's space program is devoted to the excitement, exploration of space. And we had the Chandrayaan mission in the year 2008. And till then, we had only the satellites going up to the orbit of about 800, 900 kilometers above the poles for remote sensing, or the geosynchronous satellites at 36,000 kilometers around the Earth for communication or meteorological application. For the first time in 2008, we went up to 4 lakh kilometers from Earth. We also got out of the gravity field of Earth, the influence of Earth, and finally orbited a satellite around Moon precisely and operated it for 312 days, and observations were made by about 11 instruments on that satellite. A few of them were from outside, and that also led to at least 2 good discoveries. That was the starting point that we had. In our scheme of things, study of Sun, study of Mars were important. You heard a bit of it from Professor Ajit Kembhavi, who is also a member of a Space Commission, and you will be hearing more about it later. But Mars holds certain key to the origin of life in the planet Earth. Also in the future, scientific community feel that they can go to Mars and have habitat. These are the 2 things, and Mars is our nearest neighbor. But here the issue is, it is far away, 55 million kilometer when it is closer, and about 400 million kilometer when it is farthest. To reach there, we have to go through a circuitous path around Sun, which is nearly 660 million kilometers. You can translate the distance into the communication delay. So the first and foremost issue is how to deal with the communication delay, how to ensure that we have sufficient power for commanding the satellite on its way as well as when it is around Moon. Both the transmitting system on the ground and also the receiving system in the satellite. If it takes 20 minutes for a signal from the satellite to come to the Earth to know about its health, and equal amount of time for the command, corrective signal to go up, and the decision making time on the ground, you need to provide autonomy for the spacecraft or the satellite so that it can do some minimal functions on its own, either to switch over from the main system to a standby system, or to put itself into a safe mode, or do certain sequence of operations without waiting for commands of all these actions from the ground. Instead, looking at each page, look at the index page, start that action, and go ahead. So this is what we needed to build into the spacecraft. We use some specific frequencies as cleared by the international community for such deep space missions. So we also needed to have the equipment designed for such frequencies and certain components which needed to be obtained for that. But the most important point is this kind of a mission can be done only once in 26 months when you have a specific geometry between Mars, Earth, and Sun. And in August 2010, when we started this activity, the first decision that we needed to take was whether you want to just attempt a flyby, that is a spacecraft that passes by the side of Mars for a few minutes and made some observation, or really want to have an orbiter around Mars. As Professor told, we wanted to take the challenge. The first decision that we took internally was we will work for an orbiter. A flyby is an easy thing to do. Anyway, it will pass through. But if you are able to orbit by reaching there at the right time, at the right spot, and reducing the velocity precisely, then we get the orbit that we want. So it's a technological achievement for the country. So decision number 1 of August 2010 was that we are going for an orbiter. The question is, how do we do it? You have the comparison of what US did for the Maven spacecraft with a rocket which is 10 times more powerful that they had, experience of 21 missions that they had, and they were going with a 11-year time between concept to fruition for that mission. And as far as we were concerned, in August 2010, we targeted for the November 2013 slot. Time available for the study as well as execution and the long journey was only 3 years with us. But then we were clear we are going to do it. And then, if we talk about November 2013 launch, we had to have the satellite to be ready in August 2013. After doing all the test and evaluation required to go through this difficult space environment, and we could not have any shortcuts on the testing phase, on the simulation phase, and several new tests had to be also devised for this purpose. So basically what we were now looking at a shorter time for the development of the new systems and also the integration of the entire spacecraft. Time is the essence. But then what we did was 24 hours is available for the satellite, and we put the people around, young people, many of you saw during that September 24th operation there. Mr. Arunan, who got Padma Shri just 2 days ago, was the leader of the team. He slept in ISRO Satellite Center. And all around ISRO, all the teams worked with the same spirit, and it was real war footing as far as time was concerned, without compromising on any of the quality, for a job which was a complex job. Why complex? You know, the success rate of the missions to Mars has been very, very low. And that is the next challenge that we had to go through. How to build the spacecraft without making any compromises, but realize it. And if we are able to orbit the spacecraft, then the next question is, what are we going to study? So we require scientific instruments. And to make scientific instruments, after knowing what we want to study, how to measure that, build an equipment, qualify it for this environment, especially to work for such a long period in the space, was a challenge. We took 2 themes. One was methane, because we talk about life. So our scientists came up with novel ideas how to build that sensor, methane sensor. If you say that methane is present there, then what is its origin? Is it biological or geological? There was another instrument, thermal infrared sensor, kept for that purpose. We all talk about water. To study that, the exosphere of Mars, again, 2 instruments were devised. All of you will ask this question, did we really go to Mars? What is the proof? So we thought we will put a color camera, Mars color camera. Initially, we thought the scientific value of this Mars color camera is very, very low as compared to other instruments. But what excited the whole country and the whole world is, within 1 hour of the orbit insertion on September 24th, we got the first image from the Mars orbiter, and the same afternoon it was processed, and the next day morning it was posted on the internet. So the proof of the pudding is in the eating. Many would have taken pictures of Mars from closer distances, but to get a full disk picture of Mars, that was possible with our spacecraft. And we compared the pictures with what NASA had taken, and there are very good comparisons available on this subject today. So that is what we did. So primary objective was the technology mission that you orbit. The secondary objective was conduct scientific experiments. What would be the life? We were not ready to tell what would be the life till we were clear what is the consumption of the fuel during the entire journey of 300 days. And then we said we will have 6 months life, and the life is limited by the availability of propellant for the station keeping, the moving parts which are there, as well as electronic components. So as of now, the life is much beyond 6 months. March 24th, we have completed that first phase. Now it is going to go for subsequent periods. As of now, we don't have any hitch on the spacecraft. It has worked so far well. That's the next part of it. When we talk about the communication and long distance, we had to go for 3 levels of antenna systems. One is a slow gain antenna, but large field of view. A medium gain antenna, and then that large disk 2.2 meter diameter disk that you are seeing is the high gain antenna with almost 2 degrees field of view, which finally gets operated when we are near Mars. All these were done in special frequencies that were allotted to us. Next. We had to finally get into an orbit, and our capability we found we can go for a elliptical orbit of 500 kilometers peri-apsis and about 80,000 kilometer apoapsis around Mars. How do we reach with the rocket that we have? It's only PSLV, a 4-stage rocket, which has a good reliability, which has done several missions, a versatile launcher, a reliable launcher, or with a GSLV, which is slightly more powerful but has not shown the reliability till then. It was almost 50% failure, 50% success. And it's only a 3-stage rocket with its own limitations in carrying out such missions. So we decided we will stay with PSLV. We optimized that PSLV for carrying the maximum mass, 1335 kilogram to an elliptical orbit. And then we had to design a mission in such a way that the transfer of this spacecraft from the Earth orbit to the Mars would be with the minimum energy. If you ask the students from the aerospace, they will tell you if you want to enlarge the orbit in the same plane, you consume less amount of energy. But if you want to have corrections from one orbital plane to another orbital plane, it will take more. So we stayed with an approach. It will only have the natural variations in the orbital plane. And for that minimum energy transfer, we wanted to finally get certain injection conditions, which required for every lift-off time in the every day that we talk about, we had to design a new trajectory and load it for the system. In a normal PSLV, when we do the entire mission in 20 minutes, here we had to devise the mission for 47 minutes. The long gap between the 3rd stage and the 4th stage. The 3rd stage will put the satellite into an orbit, and we had to get the argument of perigee of nearly 270 degrees as compared to 180 degrees that normally we used to have. And this is the reason we had to have the entire operation done in the South Pacific Ocean for firing the 4th stage and also seeing the separation. It was a logistics issue. How do we put 2 ground stations in the ship in the South Pacific Ocean in a difficult weather condition that existed at that time? That also we did. And PSLV did its job on November. The next one. Here the journey of the spacecraft started. The first circle which you are seeing around that December 4, 2013. December 4, 2013, this MOM crossed the sphere of influence of Earth and started moving towards Mars through the heliocentric orbit. The launch was an event, but the most crucial operation took place on December 1st morning, when we had to put it through a trajectory on that day in such a way that after going through these 300 days of journey, over 660 million kilometers in a heliocentric orbit, going through the influences of all planets and sun on a body with varying geometry, we had to reach a target of 500 kilometers plus or minus 50 kilometers on its arrival near Mars. Post Chandrayaan, the knowledge that we had would have taken us a plus or minus 66,000 kilometers on this estimation of these influences. So what learning we had is from this plus minus 66,000, we were able to achieve a plus minus 50 kilometer. That is where the mathematicians the orbital mechanics specialists showed the leadership and made us reach there. The next issue for us was, how do you track this satellite? One is to send the commands. Second one is to determine its position. And all models that we are using for this journey needed also very precise location. And when you go for such distances, you can't have diversity from stations in Earth. So we had two things. We needed diversity, means ground stations in various parts of the world. That is one requirement, deep space stations. So our station plus the stations of NASA were used for this purpose. Second one, we used a delta DOR technique, that is differential one-way Doppler ranging. We look at a quasar somewhere which is in the angular vicinity of this object, and then try to find from two ground stations the position of that, and then use that coefficients for the actual ranging. So it was a very precise determination. And step by step we went ahead and finally we did the job. So ground station also posed a complex thing for us. And during the journey from December 4, 2013 to the heliocentric orbit, and finally coming to the September 2nd week till it reached the sphere of influence of Mars, we had kept a few provisions for the mid-course correction. And the beauty of it was, even though we planned for 4, we had to do only 2 because it was going as per the original predictions. We had another very interesting problem, that is, when we have to capture the orbit, that is the time we were going to reduce the velocity very precisely by firing a liquid engine by putting the whole spacecraft in the opposite direction, which was not functioning for 300 days. And if you talk to any propulsion expert, anybody who knows about the rubber and the metals, etc., and if you look at the international experience, that is one of the major failure possibility. And we had devised our own ways of looking at this issue by having parallel paths. One path was closed after the December 1st operation. The second path was to be opened on September 24th. The question is, if it does not open and work on September 24th, there is no mission. So we also had a plan A and a plan B. And for the plan A, we wanted to be sure on September 24th it will function. And if it did not, then plan B had to be operated. So we did one important thing, and this came because we were thinking about these failure possibilities day and night. And we found we will use that main engine itself for a very short time, less than 4 seconds, for one of the mid-course corrections. And this was done on 22nd September. And on that day, when that engine worked, we were clear that this mission is going to be through. And then we had this precise orbit as we planned. We had one more challenge. If you read the articles, we had a comet coming on October 19th, very close to Mars. So that could have probably been a challenge for this spacecraft because the dust that comes out of it. So what we did was we tweaked the orbit. Originally, the orbit had an apoapsis of nearly 77,000 kilometers. And we reduced that to 72,000. So these 3.5 days of period came down to 3 days. So when the comet was passing by the side of Mars, our spacecraft was hiding behind Mars. Not only ours, all other countries' satellites were hiding at that time. So here also we got a very good experience of how to tweak. Now, if fuel is available, which is there, we can also do experiments on coming closer and closer to Mars. All these are part of the technological experiments that we could conduct on the spacecraft. But I have given 3 blocks there with white color. These are all the gains that our computational experts, orbital mechanics experts did and finally took us to that particular point. And just for your information, whatever you see in blue color is the orbit around Earth and the Earth's path. The red one is the Mars orbit, and that white path is the one that was traversed by the MOM. Now, if you look at the small ellipses around the one, that is where we used our ingenuity to raise the orbit of the spacecraft in steps from where PSLV kept it, and then starting point of our Earth to Mars transfer could take place. Whereas in MAVEN of USA, they straight came to the point where they could start the journey. So that ingenuity is using a low power launch vehicle and using the propulsion. We consume the fuel in the MOM for that purpose. Next. Before coming to that, I just wanted to tell you one more thing, because we talk about the depression, difficulties, failure, etc., etc. You look at the time in which we took up this challenge, August 2010 if you take, that is where ISRO had already a failure of the GSLV with its own cryogenic engine, April 2010. And we had behind us 3-4 GSLVs failing. In December 2010, we had another failure of GSLV. So the organization was passing through a very difficult time, with the questions being asked why GSLV is not flying when PSLV is able to do that job. And we also had several other problems which you have seen from the media. But still, the scientists, engineers, all put their might, heart, and soul, and then they realized what we have it today. So resilience, when I talked about, this is one such example. Criticisms and comments. Why are we spending 450 crores for such a mission? When others have failed, failure rate is very high, why India is attempting? Are we trying to ape others? The difference between national fame and national shame is very low. Suppose this mission becomes a failure, then what happens? Why did we not wait for the next opportunity when GSLV probably could have put a bigger satellite? Why did we not go for a bigger scientific objective? All kinds of questions were asked, but we were clear on our path. The conviction, grit, determination, and the support that we got from the government took us through, but the credit goes to all the people who really put it on 24/7 basis to reach this place. What I have put here is future, basically for you. Space exploration, we talk about planets and solar system. Astrosat is one of the major components. Human in loop, of course, this is one thing that we have started doing it, and when that crew module in December 2014 became a successful experimental mission, we have put the first step towards that. And space robotics is another area which is essential for space exploration. And when Chandrayaan-2 is going to go with Indian lander and Indian rover, we will be making the first step in that area. Of course, space manufacturing is something where we have to do further work. Space transportation, our PSLV, our GSLV Mark III, which had an experimental mission successfully done in December 2014 with the cryogenic engine getting tested on the ground successfully, which is happening today. We will have this capability for putting 4-ton communication satellite from India. Space assets, we have 26 satellites. Nobody will believe that India today has 26 operating satellites for communication, for navigation, and Earth observation. This is, for Earth observation, this is one of the best satellite constellation. It can look at meteorology, it can look at climate change, it can look at high resolution remote sensing, it can do work for disaster management, it has microwave remote sensing capability, it can look at the oceans. So this is one part of it. If you look at the communication, again, about 11 satellites and nearly 200 transponders are available today for us. And if you look at the navigation, our own system, we have 4 navigation satellites already in the orbit, which can give us the position measurement with 10-meter positional accuracy. It is India's own system. Today, you can get it, and if you put 3 more, we can have the coverage for India and around. In addition to this, the GPS system that we all know is adapted for the aircraft navigation with 2 to 3 meter accuracy by space-based augmentation. It's an operational system, a certified system which is available. Space security, there are two parts of it. The security of the space assets on one side and space for security strategic applications. Space has become the fourth dimension. Then comes communication, earth observation and navigation. If you look at the whole space spectrum today in the world, the space economy as we talk about is today 256 billion US dollar. 256 billion US dollar. And nearly 9 lakh professionals working in that in 40 countries. And of the 40 countries, if you look at the space economy part of it, India is 4th country. We have the US, we have China, Russia, followed by India. As far as Europe is concerned, they have their national programs and also the European Space Agency's program. And if you look at the per capita investment in space, India spends nearly $3 per head. Let us say 150 rupees per head. So whatever we are getting out of the space systems, these 26 satellites and the services, is essentially paid by each taxpayer, if I calculate, nearly 150 rupees per head, that's all. But if you look at what happened in Hudhud last year, or the filing in 2013, we heard only 10, 15 people dying, as compared to Divi of the 70s, where nearly 10,000 people died. That is because the cyclogenesis itself, from that stage, satellite is able to capture that a system is moving towards this direction, and then IMD can actually predict the place where it will hit, what will be the search, and what will be the area which is going to get inundated, how to move people. So you see the kind of impact it has made in the whole system. I just mentioned this because when we talk about Mars orbiter mission as one element of excitement, enrichment, etc., how it fits into the larger canvas of the space efforts of the country. And as of now, nearly 60 plus departments of the government of India and all the state governments are into application of space in their regular activities. Let me stop at this point and then we can have some interaction till the time Das Saab tells us. No, I'm comfortable standing. Maybe up to 1:30 we can.
Maybe another 20-25 minutes.
Good afternoon, sir.
Yeah.
Good afternoon, sir. I'm Arun Prasad. I'm MS Scholar in Mechanical Department. I have a question on the launch vehicles. Like we face a difficulty with GSLV, same because it's a larger vehicle, and US has larger launch vehicles. And what are the bottlenecks we have in developing larger launch vehicles? We are having very good PSLV, and why could not we go to a reliable GSLV?
Yeah, that is the question actually. When we have a reliable PSLV, why GSLV was not reliable so far? First and foremost, if you look at the configuration and compare, we have the solid propulsion system and liquid propulsion system, earth storable liquid propulsion system for PSLV. That is the main system there. When you talk about GSLV, we have an additional system that is cryogenics. But there are large number of liquid propulsion systems in GSLV, 4 strap-ons and a second stage. If you look at all the systems, the S139 booster is same in both PSLV and GSLV. PSLV has the second stage, which is liquid-based system. The same is adapted for the strap-ons and the second stage. But here one difference is there are large number of fluid components in GSLV, nearly 400 of them. And if you look at the failures of GSLV, except for the first one, which was due to a wrong calculation of the mixture ratio of the Russian cryogenic stage, the third flight failed because there was a minor error in one of the pressure regulators, one dimension. A small component, again, in the next GSLV, which is a gas motor, which stopped, and one strap-on control system got closed, and the alignment of the navigation system got disturbed. So the failure was not because of the inherent vehicle per se, it was because of the component that. This is what happens. The next failure was because of the cryogenics, that is our own new development. So the basic difference between PSLV failures and the GSLV failures has nothing to do with the vehicle configuration. That is one part of it. And we put emphasis on the reliability to ensure that from the material to the assembly process and the testing process, we take care of it. That's why in 2014 January, we had a very reliable GSLV flight. But if you look at GSLV has certain other advantages. Before the launch, you can test the robustness of the 4 strap-ons. 4.5 seconds before the liftoff, we can test it. If it is not working, we can stop the whole entire activity. That facility is not there in PSLV. And our assessment is GSLV is a far better vehicle compared to PSLV. If you look at the control system, the number of control systems, the number of propulsion systems, number of igniters, all which have to work. So per se, there is no issue with GSLV.
Hello, sir. I am Aditya Malpani from Department of Aerospace Engineering. I wish to ask, there are solid rocket boosters, liquid rocket boosters, and for any specific mission, because you have many different type of boosters, for any specific mission, how do you optimize the usage of each booster?
See, we use certain terms like specific impulse and the density impulse, etc. Specific impulse, but for the given mass flow rate, what is the kind of energy that you can get out of it? As far as solid is concerned, it would be the lowest. Then we have the liquid, earth storable. Then we have the semi-cryogenics and the cryogenics. Normally, these are used for the rockets. We have ion propulsion, electric propulsion, let me say, or nuclear propulsion, which are all used for the spacecraft missions or the deep space missions. Their specific impulse is very large, but the total impulse will be very small. So let us talk about the first 4. When you talk about the density impulse, that is a mass that you have to carry for the given energy, cryogenic is not very good candidate because you have 2 fluids which have to be handled very carefully. Semi-cryogenics and solid are considered the best options when it comes to the booster stages. Okay, this is broad. Then your rocket equation staging, that is one aspect of it. Plus, you also look at your technology, what is the pedigree that you have, what stage you have got already in hand, try to make best use of it. Just to give you an example, between PSLV and GSLV, the S139 you see in this one also. The L40 strap-ons are derived from the second stage engine, Vikas engine. And the second stage is almost similar to what you see in PSLV. This is a modular approach, so we have gained. But a small penalty you have to pay for that. Because the solid booster S139, after its activity, has to be carried by the rocket for some duration, which is a wastage really. But what you gained is a lot of development time for this purpose. So this is one aspect of it. Then if you look at the GSLV, you will see the same liquid engines with a longer duration of burning being used in the second stage. So you have to have a multi-parametric approach in optimizing what really we want to do there.
Are there plans to put man on Mars? If so, what are the additional challenges?
Man on Mars is a very, very long process for anybody in this world today. First and foremost, because of this opportunity coming only once in 26 months and the long journey involved, etc. But India has done its studies for putting a human being in the Earth's orbit. That is the human spaceflight office. This crew module is the first step. What we require is a vehicle like GSLV or GSLV Mark III, which has a reliability of 0.99. Second, we should be able to assess its health, and at least a few seconds before it is going to explode, we have to take the crew members to a safe place. A crew escape system has to be there. The crew module, what we have done is to look at the exterior, that is the thermal aspects of it as it re-enters. We require the life support system and the right atmosphere within that for the people to stay there. This is being developed at the moment. Then finally the training of the crew members, handling them, etc., etc. So we have the ability today, and we can say 6 to 7 years we should be able to do this activity. GSLV Mark III would be a good candidate for human rating. It is a far simpler vehicle compared to GSLV itself.
Good
I
one.
have a question.
Yes, sir.
Which is how far we are in the reusable vehicle mission.
Yeah, generally if you look at the shuttle of US, the Buran that Russians tried and stopped, idea is that you use the economy of the reuse. But when you talk about the overall life cycle of any reusable vehicle, we have to look at the development cost and the cost of refurbishment and the risk in the reuse of it actually. So one assessment is it is not really worth looking at as a program. Expendable vehicle will be more economical and more reliable. This is one aspect of it. Still, we are on this reusable launch vehicle technology demonstrator, because as far as technology development is concerned, it will take us to a new path, and which may become useful at a later stage, because in high temperature, hypersonic flight, etc. So Indian program is at the moment to have a technology demonstrator, and work is going on. Maybe by 2015 we will have the first test flight of it. Issue is it is a rocket, a cylindrical body, and also winged body. So the control system engineers will talk about aerodynamic instability, which is represented by a mu alpha, which is almost 20 to 25 as compared to 1 of PSLV GSLV or 5 of GSLV Mark III. That means the control system designers have to be providing a very agile system. Second one, as it comes down, again aerodynamic aspects comes into the control actually. So virtually they talk about 4 loops and also transitions. High temperature materials in different part of it. All these things have been understood today. So assembly is going on. 2015 we must have the first test flight of it.
Good afternoon, sir. Sir, I would like to hear that with the advent of private enterprises in the field of space, like SpaceX, do you think it will be a good idea for ISRO to just focus on space-based research and hand over the rocket, the business of launching rocket to some private enterprises?
We are already in this process. If you see right from 70s when we started the SLV3 and Aryabhatta, we decided that we are not going to build everything in ISRO family, but we will maximally use the Indian industry, develop them for this purpose. The result of it is today, when we talk about this Mars orbiter mission, PSLV, and the spacecraft and ground system, there are about 120 firms, starting with the Larsen & Toubro and HAL on one side, to small micro industries who contributed for this for different elements. What we are now looking at is whether they can do higher level of integration, whether a PSLV can come out of an industrial entity in the next 5 years, whether the operational communication satellites can be done through an entity of industries. This is what we are looking at. That will be a model which is unique to India, with private sector, public sector, and ISRO working together as an entity. This is on actually at the moment.
Hello, sir. I'm Radhakrishnan from Department of Chemistry. Thank you for providing the insight into this project. It's a successful project, but like I have a doubt. Every space agency starts with a mission. They have a particular vision. Of course, we are doing Mars to see if this life is sustainable over there or not. Was there any particular, if you just narrow it down, vision with which ISRO started this project? Of course, we had to face a lot of controversy and all, but was there any particular thing, aim, objective with which you started this thing?
See, if you look at the origin of Indian space program, right from 1961, when it was conceived that India should get into, the point was we had a vision that it should be finally be useful for the people and society at large. We are not going for competition like the way US or USSR went or China went, number one. Number two, it must be a self-reliant program as much as possible. These two are there. And if you look at the way the resources are utilized, about 90% are for what I said, that is for providing space-based systems for the people through communication, navigation, earth observation, etc., etc. Science is a driver whenever we talk about space exploration. And we feel, space scientists feel, anything above 100 kilometers is outer space. So explore, try to understand. But it drives the technologies. For example, the onboard autonomy that we developed for this purpose tomorrow will be useful for other satellites. It will improve the efficiency. The telescopes which the astronomers were using, you can ask Ajit Kembhavi Saab after some time. We are now looking back to Earth through remote sensing, actually. So these are the kinds of technology spin-off will come from the space science. So they are the drivers. So they need to be also. So 10% is our allotment for the space science activities as overall resources are concerned. The other part is for the brass tacks, grassroots level application program. There is no compromise on that.
Sir, I'm Ashwath Suryanarayanan from 9th standard. In the future, we need more sustainable models for rocket fuels. What do you suggest would be the alternate fuel technologies in the future, sir?
Wonderful question. I wish IIT will take you as a research student now itself. There are 2-3 approaches basically when we talk about the rocket propulsion, which is the major chunk of the load that is required to take any object to space. As I said, there are several options for the propulsion today. And what people are now doing research on is non-conventional way of taking the objects. Ladder was talked about at some point of time. So a lot of such research will take place. Instead of sending a large object, can we have smaller satellites? Then there are issues like formation flying, etc., etc. So these are all the new concepts that will come up in the future. The most difficult part is how to get out of the gravity of the Earth and take the object. Afterwards, it is quite simpler in terms of propulsion.
Thank you, sir.
Good afternoon, sir. Here. Good afternoon, sir. My question is, how much time it will take for a human, not in India or any country, to have sustainable or independent colony outside the Earth, any planet like Mars or Jupiter?
See, there are two places. One is Moon, other place is Mars. The projections are 2030, 2040, which is not far away actually, to have habitat in Moon and later Mars. In this journey, Moon may become an intermediate point for enhancing the propulsion capability, etc. This is the kind of dream actually. I have been hearing this 2030 for the last 10 years. It may not happen in 2030, it may take a few more, but the people are working in that direction. The very simple fact that there are Mars explorations and there are also the Curiosity kind of projects shows the capability of humankind on Earth to venture into such modes. India also with the lander and rover on Moon is going to get into the next step in that direction on structures and also landing there safely.
Sir, my name is Sunil. I work in IIT as a Principal Project Officer. Can you please tell us a little more about crossing the Van Allen belt with people inside, and also about space probes? Because as per our international space history, only 1 or 2 probes sent by USSR, that is the Lunar 10, returned back to Earth from outer space. All of them, they went and then they flew further away into deep space. So can you please tell us about this?
About the first aspect of it, basically all our satellites go through that issue, especially the geostationary satellites. And Mars orbiter also, when I said we went through this unique way of raising the orbits and reaching that point where it started its journey towards Mars, it had more exposure to the radiation belt. 2 things are required. All the electronic components have to be seen in that context. How much radiation it can sustain, how to do radiation hardening, how to do radiation shielding. This is what we normally do. We cannot escape that part of it. About the second part, I am not the expert to talk about, but the first part, this is what we do. In the manufacturing process itself, the silicon volume is adjusted so that we avoid this switchover from 0 to 1, etc. So many defects can come in the electronic devices there.
Sir, I'm from electrical department, and there is one sponsored guy in our field from ISRO. So he was telling that in Mars orbital mission, we have out of this 450 crores, we have spent around 90 crores for arranging, and we have outsourced it to some US agency. So since it's a 90 crore activity, and we are giving it to US. So what is our state in this this field of ranging, or how efficient we are?
Okay.
To this?
See, we require deep space network for commanding, also for finding out the position of the spacecraft. For Chandrayaan, we had 4 lakh kilometer only. Here we are talking about 400 million kilometer. So the station that we have set up in Bailalu near Bangalore, that was augmented with higher power and these new capabilities there. But when we are having a new spacecraft mission, we cannot test that first with the ground station, which is also going with the L board. Number 1. Second, if you use this station only, you will not get coverage 24 hours a day to look at the spacecraft. We were towards the end of the mission getting only from 11 o'clock in the morning till 8 o'clock in the night, the visibility from our ground station. So it was essential for us to hire on payments the NASA stations, which are in Goldstone in USA, Madrid in Spain, and also in Canberra in Australia. These are geographically at 3 locations, along with Maven. So what we did in the process is, our ground station got calibrated. Its capability was proven, and we used it for both our MOM as well as for tracking Maven. So today, along with these 3 ground stations of NASA, our station is one of the international stations. This is another spin-off that we have.
Sir, 2 days before Dr. Prasad was talking about Chandrayaan-1, at the time he was telling that the liquid propellants what we are using now, even leakage of very few ppm will cause immediate death. Are you working on any other alternatives now?
Yeah. Basically, people want to get out of those toxic propellants. Now, people are looking at green propellant. Basically, there we use unsymmetrical dimethyl hydrazine, where one has to work with a ppm of 1 ppm for safety purpose. So in handling, there could be problems, plus also the combustion products that come out. So when the semi-cryogenic propulsion system comes, especially for the booster stages, it will take out of this kind of issue. Cryogenics also, we are talking only hydrogen and oxygen basically, that will be a better from that angle actually.
Good afternoon, sir. My name is Siddharth and I'm from aerospace engineering. As we all know, all these satellites are really helpful for us, GPS and communication satellites, but we have another problem called space debris, and this space debris according to it.
No, first part of the question, can you just speak louder?
We all know that communication satellites
Okay.
GPS are all really helpful, but there is a problem called space debris, and you know about Kessler syndrome.
True.
So, in the lower orbits, at least there are 20,000 space debris which are increasing.
You are an expert. You can answer the question itself.
Varying in size. So, what plans are you have?
Yeah. So there are three elements of it. One is observation, that is cataloging the objects. Number two, the modeling part of it to see whether it will impact or come in the proximity of any of our operating satellites or as we launch any satellite. Third one, which is very complex, is scavenging. People are working on that. On the first one, today, NASA has got a system. US has a system, US Defense, it's called NORAD. And second one, we are also very capable people on the modeling. And we are also establishing in the country capability for looking at those space objects. When the multi-object tracking radar, which SHAR has built up very recently, is operational, we will be able to see the objects coming in the proximity of our remote sensing satellites. And then we can move the satellites a little bit to ensure that there is no collision. But this is an area of extreme importance. That's why when you talk about space assets and their security, this is the issue. One is natural, second one is created by someone by exploding a satellite in the orbit.
Good afternoon, sir. I am Omkar Valvekar from Department of Aerospace Engineering. Sir, as you just said that the distance and position of the satellite cause communicational delays. So what kind of autonomy was given to the satellite to overcome?
See, normally when you talk about any satellite communication or remote sensing or navigation satellite, we always build into that redundancies, that is standby systems. If the health of the primary system is doubtful, then we switch over to the redundant system. Now, today it is done for the satellite by the ground controllers. Okay. We cannot do that. So that ability we have given to the satellite. These autonomies are in some three levels, I should say. Primary one is looking at the health of a system, and then if it is beyond a threshold level, switch over to the standby system automatically. The second one, if you want to make an observation, there are a series of commands to be given, a chain of commands have to be given. Always it may not be possible to do that because of this visibility and distance, etc. So what we do is everything is programmed and kept in the telecommand processor there in the satellite. We have to only trigger which option has to be used. That is why I said instead of reading each page, you look at the only index page. This is the second level. The third level is, and the most crucial part of it is, sometimes you may not know why it has failed. It may not know how to correct it. At that time, the satellite is put in a safe mode, inverter, safe mode. That means the solar panels will be facing the sun, so power is generated. The antenna, communication antenna, is towards earth. In that orientation you put it. Then we think about it, the possible solutions, and try to upload those commands. So here that safe mode also the satellite itself will put. As far as we are concerned, we expect that state should not come, because if it is in safe mode, that means there is a major problem there. But the problem in this autonomy business is it should not take a wrong decision. So all possibilities, that what Chakravarti Sahab was telling, we have to envision that, and then we have to test and see that a wrong decision will not be taken. So we went through all those possible scenarios, a big document was created, simulated on ground, and then tried to do. That was the complexity involved.
Thank you, sir.
Yeah. Hello, sir. I'm Srinivasan from Chemical Engineering. I don't have a very technical question, but let's say we have a failure. How do you take it as an organization? How does ISRO take it if something fails? And the next question I want to ask is, if there's a failure, what is the loss in money in general?
Okay. Actually, if you see in space, the difference between a success and failure is very, very thin. And if you look at a rocket, after getting it ready for the flight, after going through all testing and reviews, etc., the only command that we can give is fire, ignite. The next command is destroy if it goes beyond a course. rest of it has to be done by all the systems in unison, in the proper sequence, proper timing, everything. So failure can occur actually. Especially when a rocket is a new one, you may not even know the full aerodynamic behavior. That's why ASLE failed, because we didn't understand the dynamic pressure at that time. Or there could be some implementation issues in the software. All these happen actually. First and foremost, we should be prepared for failures. We don't learn swimming or cycling without a failure. Only thing is that we should not die. That's all issue there actually. So be prepared for that and be transparent. Try to resolve the issue and not point the fingers at the people. If you work, there will be failure. But look at the issue, solve the problem, and tell also the country, as far as this Mars is concerned, we knew that it's a high-risk mission. Any stage it could have failed. On December 1st also, if we went in a different direction, for that particular duration the thruster worked, we will get one vector. Suppose it overperformed, we would have got another vector. Underperformed also another vector. That day itself mission would have been out actually. So there are several possibilities. But we were taking the country with us. We communicated to the country, this is the risk that we are taking. So that is also important. Towards the end of the mission, somewhere in August, September, people wrote, don't worry even if you are not able to orbit. So far what we have learned is good. So that is another part of that.
Now I know there are disappointments because we would like this session to go on and on, but we have to stop. Every good things in life has to come to an end. So also this one. Let us thank Dr. Radhakrishnan. And
Thank you.
And Professor Cheif, who told the most serious thing in the lightest possible way. I think I have seen very few sessions as successful as this one. You can see people are sitting on the floor, and there are 2 other rooms in which this is being telecast, and those rooms are also full. So. And what more a research scholar needs when somebody as experienced as Professor Chakravarti says, what a research scholar needs to do. But he ended with one thing, if you remember. It is not planned, but it has happened. He told, remember, you are being paid by the poorest people, so you have to do something for the nation.
Yes.
And this was picked up by Dr. Radhakrishnan, who did something for the nation with his team. And so, this was a great session. It's a pleasure. Maybe, I have to quit my job, but I would say one of the most successful things that I did during my tenure as Dean was probably this event. So, we have just to announce that we have a very interesting session on the future of research in India, the panel discussion. We will shift it by half an hour because, it's already 1:40. So we will start at 2:30. And Professor Kimbabi and others will be there. We will have our faculty members also. So we want all of you to come here once again and watch and participate in that panel discussion with same enthusiasm. Thank you very much.